Welcome back to Wood Engineering. I'm Jeff Arochko from Carleton University, and in this video, we're going to do an example calculation for how to calculate bearing resistance at an angle to grain. So we're not looking at parallel directly, we're not looking at perpendicular exactly, we're looking at what happens if the load is somewhere between parallel and perpendicular to grain. So we have an example structure here. We have kind of a roof-ish joist. It's fixed on the top right, it's pinned on the top right, and it's just kind of bearing on the bottom left where we have the purple bearing line. So I'm assuming that this joist is bearing on top of a SPF stud wall. And since the joist is on an angle, the load that is coming from the wall, which points straight up, is going to be at an angle to the grain of the, sorry, I should do it this way, the grain of the joist. Okay, so the load here is not parallel to the joist, it's not perpendicular to the joist, it's at an angle to the grain of the joist. Okay, so we're assuming that the reaction load at the bottom left is purely vertical because the loads on top of the joist are also purely vertical. There's no horizontal load in this example. So I've given the joist as SPF number 2, 2x10s. We're going to assume wet conditions and treated and incised lumber so we can get some practice calculating those resistance factors. And but we're going to assume a standard load duration, so that means that KD is going to equal to 1. So I think the first step of this is to take a more detailed look at the geometry so that we can look at the grain directions and what are the individual PR surface and QR surface that we're going to have to use in order to calculate the strength. So you'll recall that for calculating compression resistance at an angle to the grain, we need to calculate two different resistances, one for parallel and one for perpendicular, and we need to use some effective bearing areas in order to calculate those. So we're going to start by looking at the 2x10 geometry. Okay, so first of all, the 2x8 is 38 by 235. If you don't remember, there are some tables in the wood design manual that tell you exactly which size a member is. So this is table 11.5. It's in the second volume of the wood design manual. And I can see here a 2x10 is 38 by 235. So that's giving me my size. So I've just indicated that here, that the size of a 2x10 is 38 by 235, sorry. Okay, so let's draw the geometry and then talk a little bit about it. Okay, so I've just blown up kind of the bottom of our beam. So I'm looking at this area right here, but just blown up a little bit more so we can look in detail. And basically what we're looking at here is a beam coming in the grain. The joist grain direction is indicated by orange. It's in the longitudinal direction of the joist as usual. And here we have a load applied to that beam by the reaction. And the reaction of that beam is coming from the stud wall below. So this is going to be our NF. It's the applied load at an angle to grain. Okay. NF, in this case, we're just considering the total. I've drawn this out as a spread out load, but we're going to consider basically the one total load coming from that spread out load. Okay, and we also know that this dimension here is going to be 140. And the reason is because we have this 2x6 stud wall, and this dimension here of the stud wall is going to be 140. That's the 6 direction. Okay, like we can see that because of the orientation of the top plates, which have the crosses in them, indicating that we're looking at the cross section. The wide way is across and the short way is up and down. So 2x6 is 140 across. So that means that this surface, which fits on top of the 2x6, is also 140 across. Okay, so now what we have to do is to divide this bearing surface that's in purple into two different areas. One that is aligned parallel to grain and one that is aligned perpendicular to grain. And I'm going to have to find out what those lengths are, right? Well, how do I do that? Well, this is a right angle triangle. I'll put the little right angle in there. Okay, so we'll remember that this angle here is 30 degrees, which is what we saw up here. Okay, and so this angle in here also has to be 30 degrees. Let's blow this up a little bit further so that we can look just at the triangle for the purposes of calculating the distances. So I'm going to just draw that triangle here. Okay, so we have one that's parallel to grain and one that's perpendicular to grain. This here is, as I said, 30 degrees. We know that this side is 140, right? So then what is this side here? Right? It's sine is opposite over hypotenuse. So this is 140, right, times sine 30. Okay, and that equals 70 millimeters. And this side here, right, is 140 times cos 30 degrees, which equals 121 millimeters. So we know that this here is 70 millimeters, and this distance here is 121 millimeters. Okay, and so which side is the QR surface and which side is the PR surface? Well, the PR surface is the one that is, the surface is aligned perpendicular to grain, but the load is perpendicular to that, right? So the load is parallel to grain, right? So since the load on this side, the load is parallel to grain, right? So this is the PR surface. And this side over here, the load is perpendicular to grain, right? Because remember, the grain is like this. So it's perpendicular to grain, so therefore this is the QR surface, because QR is the perpendicular to grain strength. Okay, so now we have our geometry. What's the area of those surfaces? It's 70 times the thickness of the member, right? Which in this case is 38. So this is a 38 by, what was it, 235 member. Okay, so it's 38 in the plane, and then 70 for the PR, and then, I should do it the other way, 121 for the QR. So it's 121 times 38 and 70 times 38 on this side. Okay, so now we have those areas. Let's summarize what our strengths are. First, we're going to need FC for our PR surface strength, right? Because that's compression parallel to grain. We're going to need FCP for our perpendicular to grain strength. We're going to need KD, which we know equals 1.0 because we're talking about standard load duration. And we're going to need our KSC for our parallel strength, right? Because that's service condition for parallel. We're going to need our KSCP for our perpendicular to grain service condition factor. We're going to need our KH is going to be equal to 1.0. So even though there may be many joists here, at one bearing surface, there's only one joist. So one bearing surface cannot have like cannot share load between multiple members. Okay, so for bearing, KH always equals 1, even when we're going to calculate the PR. Like in the QR resistance equation for perpendicular to grain, there is no KH, but there is in the PR. So, but even though there are multiple joists here potentially, for the calculation of PR for looking at bearing strength, KH is always going to be equal to 1, and I have to find KT. Okay, so let's find all these things, FC and FCP. So this is it's a 38 by 235. So let me just bring up the table of strengths. We are talking about a lumber. So if I go to the lumber table, okay, first I need to figure out my grade category, right? So it's a 38 by 235. So it's structural joist and plank. So I'm going to go to table 6.3.1a. And this is an SPF number 2. So here's SPF number 2. I can read across. Parallel to grain strength, FC is 11.5, and perpendicular to grain strength, FCP is 5.3. So let's put those in. So this was 11.5 MPa from the table, And this one was 5.3 MPa from the table. Okay, now what about KSC and KSCP? So we're going to the service condition factor table for lumber, which is the one in 6.4.2. There's a different one for glulam, you'll recall. And we're talking about wet service conditions for sawn lumber, least dimension 89 or less, because our least dimension is 38. So least dimension 89 or less. So we can read down here and find KSC, the service condition factor for compression parallel to grain, is 0.69, and KSCP, compression perpendicular to grain service condition factor, is 0.67. So let's put those ones in. So that's 0.69 and 0.67. And then KH we had 1, and now we need to go to our KT table to figure out KT. So we have wet service condition. We talked about preservative treated and incised. So now we're here of thickness 89 or less. That's true because we're 38. Modulus of elasticity is 0.95. We are looking for strength properties. That falls under other properties here. It's going to be 0.85. So our treatment factor is 0.85. Okay, so that part's all done. Okay, so now we can start calculating the PR component and the QR component of these surface strengths. And then after we do that, we're going to combine them using the interaction equation for compression at an angle to grain. Okay, so let's start with the PR component. Okay, so this is the equation for strength parallel to grain. This equation in general includes buckling. We're going to assume that no buckling occurs. Our phi is 0.8, which is just a given, and then we need our FC, our capital FC, which is our modified strength. So we start with our small FC, which was 11.5 from the table. KD is 1, KH is 1, KSC we calculated to be 0.69, and KT we determined was 0.85. So our reduced strength is 6.7 MPa. Wow, that's almost, we've lost almost half our strength just because the wood is wet. So big difference. Okay, so now what is the A? Okay, that's our cross-sectional area for our compression parallel check. So if we look at the surface, our PR surface is the one in red here. And we see that we have 70 millimeters length and our thickness is 38, which is the thickness of the member. So we have 70 times 38 and we get 2660 millimeters squared. Okay, next one is our size effect factor, KZC, which you recall has a kind of goofy, I'm sure that the people who came up with this equation wouldn't like me calling it goofy. It's just a kind of empirical equation here. So this is the equation from the standard. Now, there's no real guidance about, because D is supposed to be the depth in the buckling direction that we're considering when we're calculating PR, because remember we have to consider buckling in one direction, then buckling in the other direction. Here we're not considering buckling at all, so there isn't really any guidance about how to calculate KZC because there's no buckling. So I'm going to use the worst case values for D and L. So I'm going to assume size effect factor for buckling in the strong direction. So D is going to be 235. And L is going to be the length of my, the overall length of my member, which should give me a conservative value here. I mean, I think they should put something in here that tells you what you should consider for KZC, since this is a local effect and not an overall effect. I mean, it seems like you should probably be able to consider that KZC equals 1, but there is nothing for that in the code. So just going to make a small note about that and then finish it. Okay, so how do I know that the biggest values of DNL are the worst case? Because it's a if you plug in different values of DNL, you'll see that as the size becomes bigger, as kind of the size, as the size becomes bigger for size effect, the size effect factor goes down. So you remember, usually for bigger members, we get bigger size effects, which means we need to decrease the strength. And you can try that on your own, plug in different values of DNL. See, as I put bigger values, I'm going to get a worst case. So D, I'm going to pick the total size. Even though I'm only looking at a 70 millimeter piece there, since this is a size effect, I'm going to consider the full size of the member. So D is going to be 235. L is 3,000 divided by cos 30. That's because my member here is 3,000 in the horizontal projection, but it's actually a diagonal member. So I'm going to consider that angle, which makes it a bit longer. 3464 millimeters. And don't forget that when I plug these values into the equation for KZC for lumber, I have to put them in as millimeters or it will not work. Okay, so I plug those in and I get a KZC of 1.07, which is less than the limit of 1.3, so that's fine. And my KC, I'm instructed to use 1.0 when I'm calculating bearing check for KC because there can't be any buckling because we're looking at a local crushing effect. That doesn't mean that the overall members cannot buckle. The portion of the load that's axial to the member, I will still have to calculate the overall member compression buckling strength. That'll just be a separate check. Since I'm only looking at the bearing strength in this equation, I'm not considering buckling. Okay, and when I sub all those in, 0.8 for phi, 6.7 for my modified strength, 2660 for my area. That's the small little area that I'm applying my compression parallel to, the 1.07 for my size effect, and 1.0 for my buckling, my slenderness factor, I get 15.3 kilonewtons. Okay, so that's my PR component for checking compression at an angle to grain. Now I have to do my QR component. So I'm using the effect of all applied loads QR component here because I can't get squeezing really easily when I do this individual check. I might still want to check squeezing if I have a significant load on the other side of the member. But for now, I'm going to leave that out. Okay, so the first step is I need to find my reduced strength. So I get 3.0 MPa. Again, this strength is reduced almost to half. So I started with something pretty small, which was 5.3, because compression perpendicular is much weaker than compression parallel. And then I modified it for wet, and I got 3 MPa. Okay, so now I'm looking at my bearing area. Okay, and my bearing area here is this area, right? Because I'm looking at the load that's acting, the portion of the load NF, basically, that's acting in the perpendicular to grain direction. So I have 121 millimeters times the thickness of the member, which was 38. So this is 121 times 38. I get 4,598. And my KB factor for this equation is 1.0. Why? Because this load is being applied at the end of the member. So there cannot be any of the kind of trampoline effect factors that we have seen before. And the KZCP, the joist, is aligned vertically at the location that we are bearing. So there, we're not applying it on the flat. So KZCP is definitely going to be 1.0. Okay, so now we can calculate our QR. So QR using the equation above. Phi times strength times bearing area times KB times KZCP, and I get 11.0 kilonewtons. All right, so now I have my parallel component, I have my perpendicular component, and actually I probably did those in the reverse direction because my video's flipped. But anyway, we have both components, and now we can use the interaction equation to calculate total resistance at an angle to grain. Okay, so you'll recall that the total resistance at angle to grain uses this equation, which is an interaction equation, which is going to come up with some strength that is somewhere in between the parallel to grain strength and the perpendicular to grain strength. And we need to figure out what theta is here. Okay, so I'm just going to draw a picture so that we can work it out a bit more explicitly. When in doubt, draw a diagram. Okay, so the load is, so the angle theta is the angle between, it's the small angle between the load direction and the grain direction. So here I've drawn the load direction. The load direction we know is vertical. The grain direction we know is aligned with the, I keep doing this the same way. Yeah, is aligned with the longitudinal axis of the member. So our angle here, theta, is not 30. It's 90 minus 30, which is 60. Okay, so don't get confused. One trick is, you know, whenever I'm drawing these, you know, like say I had 40 degrees and I was trying to figure this out by drawing a diagram. Just as an aside, one trick to figuring this thing out is when I draw things like this, I'm trying to figure out what angles what I do is I draw it at kind of an exaggerated angle. So if my angle was 40 and I was trying to decide between 40 and 50, I'll draw 40 like as if it's 20 degrees. I'll draw it super shallow. And because that way I can figure out, just based on what angles are small and what angles are big, which angles are going to be 20 and which angles, or sorry, which angles are going to be 40 and which angles are going to be 50, for example, just by looking at which angles actually look like 20 versus 70, you know, if I've drawn it really exaggerated. So when you're trying to figure out angles, it's nice to draw a picture that is exaggerated. So if I have a big angle, draw a really exaggerated big angle. And if I have a small angle, draw a really exaggerated small angle, and it makes it really easy to figure out which is which. Because I can tell here, obviously theta, like I know that that's theta because it's the angle between the load and the grain direction. I can obviously tell that theta is not going to be 30 because you can tell that it's a big angle. It's not a small angle. Okay, so therefore theta is 60 degrees. Okay, so now I can calculate my NR. So I have my PR, if you recall, is 15 kilonewtons. I have my QR, which is 11. I'm putting these in as 15.3 and 11 instead of putting them in as newtons because in this equation, all the units cancel out. I mean, not all the units cancel out, but the bottom units will cancel half of the top units, right? So I have kilonewtons squared on the top and I have kilonewtons on the bottom. So I could have done it in newtons and had newtons squared on the top and newtons on the bottom, and I'll still end up with the right answer in the same units. So sine squared 60 plus 11.0 times cos squared 60. We recall to make sure that our calculators are set to degrees if we're doing this in degrees. And you know that sine squared 60 is just sine 60 squared. And we get 11.8 kilonewtons, which, as you can see, is kind of part way between 11 and 15.3, but it's closer to 11. And that would be because of the angle bias in the direction of there's more area that is being loaded perpendicular to grain than parallel to grain. Like you can see that that's the case here, right? The orange is much bigger than the red. Okay, so we can compare that now to NF. If we have NF, we're going to compare it. I'm just finding the resistance right now, so I don't actually know what NF is because it wasn't given. So that gives me the strength for the joist in bearing. So the joist is coming in this way, and it's sitting on the bearing. No, the other way. Anyway, forget it. It's the strength of the joist. Now, I also need to check the strength of the top plate, right? So for the 2x6 top plate, okay, because at the bearing surface, the top plate, like the wall below, loads the joist, but the joist also obviously loads the top plate. So I can draw that geometry. Okay, before I talk about this, just one note about the NR, because this NR is, the NR here is compared to basically the vertical load, right? The vertical load was our NF. I just wanted to make sure to mention that. In this case, the vertical load was our NF, and we labeled it as NF before. So I'm comparing that NR to that NF. Okay, down here, so we have again NF in the other direction, right? It's basically the vertical load from the joist onto this, the top of the wall assembly here. And we need to figure out all the same things. We need FC, we need FCP, we need KD, which we know is equal to 1.0. We need KSC, we need KSCP, KH we know is equal to 1.0, and KT. Now, in this case, our 2x6 is, or sorry, not, yeah, our 2x6 for the stud wall is this one here. It's a 2x6 SPF number 1. So let's just check the strengths for that. So a 2x6 SPF number 1 is going to come from this table. So here is SPF number 1. We have strength parallel to grain is 11.5, which was the same as we had for the joist, which happened to be number 2. And the perpendicular to grain strength is 5.3. So these are the same values we used for the joist. Number 1 and number 2 have the same parallel to grain strength. And also notice here that perpendicular to grain strength has no effect of grade. So all of these grades have the same perpendicular to grain strength of 5.3. Okay, so let's go back and fill those numbers in. FC is 11.5 MPa. FCP is 5.3 MPa. Okay, and these KSC, KSCP values all also happen to be the same. And I'll leave, if you want to confirm that for yourself by going back to tables, you can. These are all the same as before. Okay, so now what's the load resistance here? We're only loading perpendicular to grain on the top plate. So if this is my top plate, my load is coming here. Okay, so it's in a perpendicular to grain direction, not in a parallel to grain direction. And it's not at any angle to the grain. It's completely perpendicular. So there is no interaction that needs to be done. We're doing a regular perpendicular to grain check here. And you'll recall that this is our equation for that. AB, KB, KZCP. Okay, so we have 0.8. FCP is the same as what we had before. Okay, so I didn't actually do the calculation here. It's the same calculation as we did previously. We have 38 by 140. 140 is the width of the top plate, and 38 is the thickness of the joist that's sitting on top of it. So that's the interaction surface between the two. 1.25 is our KB. Without going into detail, we can use KB because we're not at the end of the member. We're not in a high bearing stress area. And we have a 38 millimeter bearing length, which is along the length of the member, the top plate. And we have a KZCP of 1.15 because we have width over depth greater than 2 because we're loading that top plate on the flat. Okay, so we do all that and I get 41.0 kilonewtons. So what's the total resistance of this joint? It's going to be whichever is the lesser of the resistance of the top plate versus the resistance of the joist, right? It's because they're both interfacing at that location. So if I continue to increase load on this, it's the joist that would fail in bearing first before I would have any problem with the top plate, because the top plate strength 41.0 is much, much greater than the angle resistance of the joist, which was 11.8. So the resistance of the joist governs the design. So nice to put a final statement of what is the resistance of the bearing surface overall, which in this case is 11.8 kilonewtons. And that's the end of this example.